So again, thank you very much for inviting me. Today I will talk about undergraduate course allocation through competitive markets, and you will see why we have the word undergraduate in our title, which is distinguished through the course allocation at MBA schools or some other course allocations. So this paper is joined with Daniel Kornbluth, who is a PhD student at Harvard University, and I very much recommend him. He's an excellent researcher and very good co-author, excellent co-author. So in this paper, we'll talk about the course allocations. And course allocation in undergraduate institutions actually differ by country. So in many cases, it's based on the culture. In some cases, students actually do not choose courses. So, for example, in France, only few courses can be chosen by students, and only at the later years of study. They rather choose major rather than courses, and once major is chosen, basically the path is clear what kind of courses you're taking. Another extreme is actually United States, where students starting from the first semester can pick 1-2 courses out of 5. And this is kind of the courses they really want to pick, to explore. It can be from the same department, different department, and there is quite a big amount of choice. And of course, if the students can choose the courses, this creates the issue of oversubscription of the courses, and how this oversubscription should be rationed in the best way. And here where our paper comes, or market design in general, how to allocate the course seats to oversubscribed courses. And this is what I'm going to talk today and to present. By the way, feel free to interrupt me with the questions by raising the hand or directly interrupting. Let me first motivate that the problem of course allocation is very important. So let me just read it. A quote from Daily Californian. This is a Berkeley magazine. Forget Facebook, delete Tinder. What even is Instagram? California Central is our latest online obsession. The start of a new semester means that everyone is hunger gaming the crap out of class rosters. We obsessively check California Central every 400 seconds in hopes that we will have moved up on a course waitlist. Full classes mean stressful waitlists, and waitlists mean emotional turmoil. And this is just a quote, and I completely agree with the quote at Carnegie Mellon University, where I come from, where I'm currently in. It's also very much courses are contested, and there is a lot of emotional turmoil if students cannot take some particular courses, or even if they just end up on the waiting list. But not all administration actually can handle waitlists correctly, or also provide the students with the courses. And this is another quote from the same Daily Californian that shows that some students, they decide to take the matter in their hands. So in particular, one of the students, and this is only one of the few quotes from the one of the few students who actually posted the same message on the Facebook. He basically said that I'm ready to pay $100 to the first 5 students who will drop a particular course. So he is probably on the waiting list. He wants to get in, and he is ready, really ready to put the money on the table in order to make sure to get this particular course. In many cases, this is students who are on the last year of study, or visiting students, exchange students, who basically say, if I don't take it this semester, I would never take this course. So the problem of course allocation can be quite important, and courses can be quite contested at some universities. Actually, we did research for the top 30 universities according to US ranking, and many of these universities follow approximately the same process. There are some small differences and subtleties that I'm happy to talk offline, but basically most of these universities follow a random serial dictatorship with course reserves. This is kind of a name that we will put, and let me describe it a little bit in more detail. So each student at most of the universities in US and even actually abroad, so I saw Antonio Ramiro Medina is also joined, so he can also confirm this happens in Madrid, that they receive a registration time. During this registration time, or starting from this time, they can log into website, see available courses, and among available courses, choose. And potentially also put themselves on the waiting list. This is quite straightforward process. They don't need to strategize. They see available courses, go. Registration times are not, however, completely randomly assigned. In many cases, there is a priority based on seniority of students. So more senior students can choose earlier. There is also department-specific priorities that are implemented through the course reserves, seat course reserves. So basically, a specific number of seats is reserved for specific groups of students. Like you have, say, Principles 101, and say half of the seats reserved for economic students, economic principles. Of course, there is a role of waiting lists, and because of the seat reserves that are relaxed during the process, cancellations, and other factors, there is a waiting list. Waiting lists are settled differently in different universities, and in many cases, it's completely decentralized process, which results in many inefficiencies, at least at the university that we look at. So we don't want to go into that kind of second stage process, the waiting list reserves. We want to concentrate on the main one, how to assign courses during the main course allocation process. But again, I'm happy to talk more how the presence of waiting lists influence the whole process. So serial dictatorship with course reserves is a nice process. It's a strategy proof. There is no much strategizing, but it suffers at least two problems. The first is selection of seat reserves. You can imagine the selection of seat reserves is done ex ante, and exactly guess how many seat reserves we need may be problematic. If you over-reserve, it means you need to assign the seats afterwards. If you under-reserve, it means the underrepresented groups, or the groups that you want to target, some of the students from these groups might not be able to take the seats in the class. So for example, let's consider a computer science student who are interested in market design, but market design typically at Carnegie Mellon reserves 90% of seats for economics students. Well, in some cases, some bad years, maybe economics students can fill only 70% of this. In this case, some computer science students want to take the course but cannot, despite seats being open. So either you don't allocate it, which is a waste, or you need to allocate during that centralized process. The second problem is vastly different outcomes among similar students. So consider two students, Anne and Betty, and assume these students, they're friends, they joined university together, they're from the same department, from the same year. It's perfectly possible that Anne has a 9 a.m. registration time, and Betty has a 5 p.m. You can guess who can get all popular courses and who can get neither of the popular courses. So there is a huge literature on the matching markets, and there is some literature on course allocation. I will not stop here for a long time and go paper by paper. The only thing I want to present that our contribution compared to two papers. One is the paper by Eric Budish, 2011, who developed a deterministic allocation mechanism using the pseudo-market equilibrium, where you allocate courses to students in absence of priority. So this is basically the target is MBA course allocation, and his mechanism has been implemented in the bunch of business schools, I think around between 5 and 10. I forgot exactly what Eric mentioned last time to me. But compared to this mechanism, our main contribution is basically to introduce priorities that are present in the undergraduate course allocation. So in the MBA setting, so all students have the same priority to all courses, but in undergraduate, it's very important. As I mentioned, the common priorities based on the seniority or year of study and department-specific priorities. These are most two typical priorities that we observe. However, priorities were studied before. So by Yongao here, Antonio Morales, and Marek Pitch and Jan, they consider setting with priority in many-to-one setting, matching markets, and random allocation. So compared to them, I think we push the boundaries to the deterministic ones. And I will be more specific what I'm talking about. So just to have an overview, we developed a deterministic pseudo-market with priorities mechanism that allocate courses to students based on students' cardinal utilities and respect course priorities. We show that this mechanism has a desirable property in approximate sense in terms of stability, efficiency, fairness, and strategy proofness. We also have actually the university data. Using this university data, we calibrated a student's utility model. Basically, we calibrated their preferences. And using this model of the preferences, we use simulation to compare our mechanism with a better version of random serial dictatorship, a better version, more efficient compared to what is used in practice, and two versions of deferred acceptance mechanism. And we show that our mechanism delivers a larger utility to most students with a larger average utility and a more ambient equal course allocation. So we'll pause here and grab a clock. Oh, I have a clock here, just to make sure that I'm going on time. So let me know if you have any questions. And again, maybe I cannot see raise the hand. Okay, good. Okay. If you don't have any questions, let me proceed and explain in more detail. So this is a plan for the talk. I will talk a little bit about the model. Then I will briefly mention our theoretical results about the preferences of our mechanism. Then I talk a little bit about the university data and talk about simulations. We also compared not only with deferred acceptance and random serial dictatorship, we actually consider more mechanisms and much more simulations. But again, I'm not sure that I will have time to talk about it, and feel free to look at the paper. Okay, let me begin. And again, feel free to interrupt. I want to make sure that everyone on the same page. And if you have a question, I bet somebody else also had the same question. Let's denote S as a set of students. This is a calligraphic S, and S is a number of students. C is the set of courses, and we denote, for some notation reasons, M as a number of courses. Each course has a capacity, number of seats, which is denoted as QC for each course. We allow quite general preferences. So students have preferences not over individual courses, but over individual schedules. So it's a combinatorial problem. So they really can have some complementarities or substitutes. But we assume that students can take at most K courses. So K, whenever you see K in the paper, in the presentation, it's 5. Think about it, it's 5. So it's a bounded number of courses they want to take. This is more or less correct in the data. In the data, only 5% of the students take more than 5 courses. This allows both complementarity and substitutability among courses. One important feature of our paper is the presence of priorities. We model as a priority is basically a number between 1 and R, and think about typical R is 8. So it's a course priority. There is a huge tie breaking going on. So, and R, which has a subscript S as a student and C as a course. So it's a course and student specific. But again, there is a lot of tie breaking going on. So for example, let me give you an example of typical priority, and you will see the degree of tie-breaking. And our notation is that a larger number means a high priority. Questions? Okay, so let me give you an example of priority structure. Typically, as I mentioned in the beginning, in the introduction, we have a combination of two priorities that we observe in the data. So it's year-specific priorities. Students who are closer to graduation, they have a higher priority, and department-specific. So we prioritize students based on the course department. So if you're from the same department as a course, you have a high priority. This is two priority structures. They can be combined in various ways. From the talking to various departments and also looking for websites, there are typically two ways how they are combined. We consider one way, and the other way is also in the paper. So the first way is when the year-specific has a precedence over department-specific, but you can also imagine a vice versa. So for example, for one possible priority structure is that the fourth-year students inside the course department has the highest priorities, then the fourth-year students outside the course department, then the third year inside, third year outside, and so on. So this is a typical priority structure. So as you can see, there are only 8 priorities, and there are thousands of students. So for example, at Carnegie Mellon, there are 8,000 of students. So you can imagine there are roughly around 1,000 students per priority. So there should be a huge tie-breaking going on. And if you go for a higher university, then of course, the degree of tie-breaking is even larger. So an allocation assigns a course schedule, XS, that basically is m-dimensional vector of 0, 1s, and it's easy to understand the notation. So if it's 1, then the course assigned to the student S. If 0, it's not assigned. An allocation is feasible if the total number of assignments is less than capacity. But does an allocation need to be always feasible? No, we allow for some errors. So for example, we denote the excess demand for course C as a maximum of over subscription and 0, right? So some courses can be oversubscribed, and we try to minimize this error. So that would be clear on the next slide. But before I move on, so the next slide will present our mechanism, and then I will talk about the properties. I want to make sure that notation is clear. Okay, so let's talk about the pseudo-market with priorities mechanism. So let me first quote informal description, and then I will be precise with the mathematical formulation. So what we really ask from students is their preferences over course schedules. So this is only input. So they don't need to, they need only think about carefully what kind of preferences they have over course schedules. This can be itself a very difficult problem because it's a combinatorial elicitation problem. So currently how it's done in practice, you submit preferences of individual courses, like number between 0 and 100, and numbers for the limited complementarities, say for bundle of the courses. But the recent paper by Somalis, Zamanlou, Weinsteiner, and Sven Suiken, they actually developed machine learning techniques in order to better elicit the preferences of a course schedule through the inquiries. So this is, I think, how should be done that. But again, we'll leave it to them how they elicit preferences and only analyze the allocation methods. Then once we ask students for their preferences, inside the algorithm, students are randomly assigned budgets of fake money with small inequality. So it's number between 1 and 1 plus beta, where beta is some small number. And then we know their preferences, we know their budgets. Now we change the prices, and the prices now the course and priority specific. I will be more precise in order to balance basically the demand for the courses and the capacities. So we basically use a version of Tottenham process in order to find an equilibrium. However, one important thing, we don't allow any kind of the prices. So first of all, prices are priority specific. This is different from, for example, Eric Budish paper, where the price is a course, only per course. We have per course and priority. But also, we require that for each course that has several priority levels, there is a cutoff level. Students with a higher priority face a price of 0. Students at cutoff level, some number between 0 and 1 plus beta, and students with low priority, this is basically infeasible. Why we need it? Well, this will, as I will try to explain, allows basic notion of a stability. So in the sense, there will be no priority evaluation, there will be no justified envy. And this priority structure will allow that. Okay, so let me briefly, and we allow market to clear with some error because we're trying to find the market equilibrium in the presence of indivisibilities. So it's not random allocation, it's deterministic allocation. Plus, there is additional difference from the standard general equilibrium. There is also a situation, right? Preferences have a situation. So you don't want to take more than 5 courses. Once you have 5, you're done. And that's also a big difference compared to the general equilibrium literature. So let me be more precise. So we have an alpha beta pseudo-market equilibrium with priorities. What is it? It's an allocation rule. This is the price. This is a budget. Budget satisfy inequality. So beta is basically, beta is a degree of budget inequality. Then inside the mechanism, then the allocation maximizes student preferences given their budgets and prices. And the prices are course specific and rank specific, priority specific, and there is market clearing error. One important thing that we say that market clearing error can basically it's excess demand, whether it's positive or negative, if the prices for the lowest priorities is more than 0. But we only count excess demand if the prices is 0. And intuition for that is the following. So assume we have a course, I don't know, some very unpopular course, and not enough students enrolled. Well, probably it's fine. We don't need to consider as an error, just not enough students. But in this case, it's better that price be 0. If the price is positive and there is still some seats left, something is wrong here. So that's the only question why we need this adjustment. And as I mentioned, there is a cutoff pricing. So there is a cutoff level, R star, for each course that determined endogenously, where the price is between 0 and 1 plus beta. For all larger priorities, it's 0, and for smaller priorities, it's larger than 1 plus beta. Any questions? Okay. Yeah, feel free to interrupt me. So first of all, what we have is an existence. So in general, existence is not guaranteed because the demand for any price vector jumps discontinuous. So for example, if I and say Patrick want the same exactly courses and we have the same exactly preferences, then for any prices, either we demand this course or not demand this course, right? Under the condition, that we have also the same budgets. That's why the presence of budget inequality allows me to break the ties. Also, there is a complementarity and substitutability going on. That's why we need to allow for some market error. So what we first wrote is that for any budget inequality, maybe really small, we really use it as a tiebreaker. There is an square root of km over 2 and beta. So the first term is exactly referred to alpha, is a market clearing error, pseudo market with priorities. And as a reminder, m is a number of courses, k is 5, and over 2. So this actually error, square root of km over 2, is exactly what Budish had in their paper. And it was for us, honestly and originally surprising, because he talks a lot about the fact that the intuition for this market clearing error is that it should be proportional to the dimension of price space. But in our case, the price space has dimension m times r compared to m-dimensional space in Budish. However, how we get it is using the cutoff pricing. So actually, cutoff pricing effectively allows us to reduce the dimension to m-dimensional space. Let me illustrate it quickly. I think this is maybe one of the few illustrations. So imagine you have a course, you have 3 priorities. In general, there is a price for each priority. Probably there should be some monotonicity involved. Of course, the students with the high priority should be low prices, but what we require is really cutoff price. And this cutoff pricing can be implemented through restricting the search for the prices to one-dimensional, set. So think about the zero price, say everyone at the origin. When the price is sold at 0, well, that's fine. For everyone can demand. Then we slowly going up and increase price for the lowest priority student, PC1. We increase it until 1 plus beta when this priority cannot afford the course. Then we keep it there. The first priority cannot, but for everyone else is 0 price. Then the second one, we increase the price for the second priority. Now the first priority cannot, second is rationed. So basically any price between 0 and 1 plus beta is the amount where you have a ration. You ration part of the students at 1 priority. You also increase to 1 plus beta, and finally for the last. So that's an idea. So we look only in this space of this in this space of the pricing that's restricted to this line. That's the intuition why we managed to decrease the error to the Eric Budish case. Now let's talk about the properties, if you don't have any questions. Of course, the first property that we want to get is stability. And stability comprises typically in 2 elements, individual rationality and having no blocking pairs. But there are some problems why we, even cannot get there. And the problem here, why we cannot get exactly stability is the presence of market clearing error. Presence of market clearing error suggests that there are some courses that oversubscribed. There are few of them, but there are. And some courses undersubscribed. So there are some available seats. We aim to get a very small amount there, but it's there. That's why we cannot get basically the feasibility, the problem with the feasibility. And I can see, I think somebody has a chat. So the question is from, does a computer calculate the equilibrium, or do students actually buy courses with fake money? Computer calculates the equilibrium. Sorry, I didn't see it. Probably the question was early. I apologize. So instead of exact stability, we introduce a new notion, which is called approximate stability, which is if the allocation is approximately stable, if it's stable in the environment with courses adjusted capacity to exactly capacity that we found in equilibrium. So, and this approximate stability precludes any justified course envy, but of course there are some seats available and maybe I want to take it, but designer doesn't allow. Or maybe there are some seats that oversubscribe for some courses and feasibility is violated. So these only violations are allowed. And again, the main thing why we were able to get that the outcome of our mechanism is approximately stable is a cutoff pricing. So basically, cutoff pricing excludes the possibility of blocking. Justified envy among course participants. Now we also want to talk about efficiency. A feasible allocation is Pareto dominates a feasible allocation. Why? If there is at least one student who strictly prefers your course schedule and all other students weakly prefer. However, in our case, we have this priority constraint. Somehow we need to respect them. In general, there is a well-known trade-off between efficiency and stability. So we really want to go for constraint efficiency. But whenever we keep priorities, we need somehow a notion. What does it mean to keep priority? Priority is over individual students. And we want to have some notion of a priority of a group of students. That's why we borrow basically from the literature, the notion of respecting priority through the first order stochastic dominance. And this is has been done in the Chen and Ghosh, Schlegel, Mamagashvili, and Kornbluth, Tertier, Terrier, and Udkunver. And we call an allocation is approximately priority constraint efficient if for each assignment Y that Pareto dominates and has the same number of the assigned seats for each course, there is a course C prime that basically violates this respecting priority as much as another course. So if we find a better allocation, should violate. However, we also added the same number of the total seats assigned is exactly as we did it for the stability notion. It means we want to eliminate slack. We want to eliminate this error that is present in the course allocation. And what we showed that every pseudo market with priorities is approximately priority constraint. Questions? Okay, so what is important and I think insightful, and this is what exactly absent in random serial dictatorship is a fairness. As I mentioned at the beginning, it's perfectly possible if we consider Daniil and me, we assume at the same priority, that Daniil can get all desired courses and I get none. This is really problematic, and talking to practitioners, they really didn't like it, this inequality. Our mechanism fights with that. So the presence of justified envy, if Daniil were a high priority, if the Daniil were a higher priority than me, Daniil would not envy my course schedule. This is justified envy or proximate stability take care of. However, there is thousands or at least hundreds of students of the same level of priority. How to make sure that students do not envy each other, or there is at least limited envy? Well, of course, I cannot get rid completely of envy, because if Daniil has exactly the same preference as we, and there is a limited amount of courses, so Daniil wants market design and I, at the end, somebody is assigned. If Daniil is assigned, I will envy. However, what we can guarantee is the envy bounded by a single course. What does it mean? An allocation has a schedule envy bounded by a single course among students of the same or smaller priority if we consider two students, and we can weekly compare them in terms of rankings for all courses. Then either student S likes his schedule as much as the other student, or they exist at one course. If the other student drops, he already not envies. So he likes his schedule. So in some sense, this is a limited amount of envy, which is also present in the Eric Budish paper, but without the quantifier among students the same or smaller priority. And for the small budget inequality, less than 1 over k minus 1, k is 5, so it's less than quarter. Pseudo market equilibrium with priorities has envy bounded by a single course. among students of the same or smaller grade. So this is a nice property of a pseudo-market equilibrium that cannot be guaranteed by random serial dictatorship, and we'll see also later by deferred acceptance algorithm and many other algorithms used in the literature. Questions? Okay. So last property before moving to the empirical part, what I want to talk about is about the strategy proofness. Our mechanism is not strategy proof, but it's strategy proof in the large. So easy putting that strategy proof in the large, it means that the students, if they cannot influence prices, they should report preferences truthfully. And if you can think about it, again, if they cannot influence prices, then what the algorithms on their part provides a maximization problem. It solves a maximization problem. It actually solves like thousands of maximization problem at each iteration. The only thing quantifier if it cannot influence prices. So the only way is how to influence is through the prices. And I want, for those who know auction theory, I know that there are many of you know auction theory very well. So whenever you have multi-unit auction, the typical way how you can manipulate prices, you decrease the demand for your units, right? By decreasing, what happens? Well, maybe you don't get some units, but those you get as a smaller price. Here, this does not directly works, because if you drop the demand for some courses, well, maybe the price drop, but you don't longer demand the courses. That's why there is a way to manipulate, but this typical manipulation does not, at least the manipulations are not that straightforward. Okay, so let me talk a little bit about university data. Again, I'm presenting, I don't want to offend anyone, but I have just recently found the quote from Angris and Pishke: if applied econometrics were easy, theorists would do it. So it doesn't suggest that applied econometrics is easy. Honestly, it's not, but theorists can do it. So we have a data on the students from some Mid-Atlantic University. It's around 6,000 undergraduate students and 756 courses. There are 41 student departments, 42 course departments, different number of departments. Just some departments use just for classification of students and some other for courses. That's why it's a little bit different. There are 7 colleges. So what is important is that information about our subscribed courses, because in general there is no role for market design if all courses are below capacity. It's very easy case, and we believe in some university that's exactly happens. Only few courses are at capacity, so there is no need to rationing or designing any mechanism. Students just pick their best courses. That's it. What's to design? The only problem of the design, market design, it happens if some courses are at the limit, and this limit cannot be enlarged, or the capacity can be enlarged. So in our data, approximately 11.2% of the courses at capacity. We were very much surprised to observe, but actually quite a substantial number of courses enrolled above capacity. And first we thought the capacity should be hard constraint, like class size, but then we figure out it's not. In many cases, it's done for many other reasons, for better class dynamics, to make sure that the different courses have approximately the same size, so many other things. So that's why some courses has oversubscription. And this is in line, I would say, with what we observe or what we obtained from our mechanism. We also have some error of overcapacities. And you will see, I will present the error, it's much smaller than what we observe in the data. So actually, it's fine to have some oversubscription. Right. In general, we don't have a course priorities from the data. rather than we have a course reserves. So this is an example of course reserves. Say, for example, let's consider, I don't know, the second one, real analysis. There are 50 seats reserved for year 3 and 4 students at Department 2. So using this data, we create the priorities. How we create the priorities? Well, we call it hybrid course priority structure. There is always year-specific priority. As I mentioned in the beginning, what happens in all universities that senior students choose earlier, so they have a higher priority. And there is a department-specific priority that prioritized based on the course reserves. So, for example, this real analysis that we have Department 2, year 3 and 4, and 50 course seats. First of all, we forgot about total reserve seats at all. And we create this priority structure. So the first year students in Department 2 has the highest priority. Fourth year students in all departments except Department 2 has a 7th priority, and so on. Since there are no reservation for year 2 and 1, we leave the corresponding places empty. And by the way, you might have a concern why we completely ignore information about total reserve seats. We don't. That's why we consider some other mechanism where basically considers only priority for this specific number of reserve seats. But again, I don't have time to talk about it. That's why let's ignore it for now. We just create this priority and we will run deferred acceptance and our mechanisms. Any questions? I will try. Okay, we also don't have a student preference. That's really tough. But we really know the whole course allocation process. We basically know second by second which students are enrolled in what courses. And since we know also the process, which is random serial dictatorship with course reserves, we calibrate the model. We consider parametric version of the model that has student horizontal component corresponding to student-specific preferences, vertical quality terms corresponding to the value of the courses, and also interaction terms. We calibrated using method of simulation moments, or simulated method of moments. The biggest challenge here in the calibration, and that was important part of the process, that actually enrollment is at the maximum capacity for some courses. It means that for some courses, at least fixed effects, only partially identified. So if you increase, say, the value of the space effect, it doesn't change the enrollment. Our solution, due to the presence of the data, we are able to calibrate them using how fast the courses are enrolled. Because we know which students are enrolled in which courses. Basically, the more popular students, more popular courses should be enrolled earlier. That's how we solve the problem. But again, I'm happy to talk more about it afterwards if you're interested. Any questions before I move to the simulations? Okay, so we do simulations. So we know that pseudo market with priorities has some nice properties. But why to do simulations? Well, first of all, these properties have to communicate to administration. Second of all, it's of course nice that we have these nice properties, but typically what administration cares and asks, what the percentage of students will be better off or worse off? Of course, we have one mechanism and switching another mechanism. There is a limited number of resources. Some students will be better off, some students will be worse off. And we want to make sure that more students are better off and not so many is worse off, right? Also, we have a nice properties in terms of a fairness for our mechanism, but we don't have a nice properties and how to judge on random serial dictatorship. We don't know how unfair is it, or we don't know how many students will end it. The same for deferred acceptance and other mechanisms. We don't have these properties. We use simulations to update. And of course, another thing is very convenient to compare our mechanism to other mechanism is just simulations. We can program like 6 other mechanisms and compare the outputs. So one thing what I should mention is that the typical course allocation process in many US universities, as I mentioned, resembles theory dictatorship with actual course reserves. But what kind of course reserves to consider? We first took course reserves that we observe as real, but the problem is that nobody restricts how these course reserves are picked. Typically, department administration is responsible on how many course reserves should be reserved. And of course, what they do, they want to make sure that their students get the courses in any possible outcome. That's why this leads to very large course reserves. They just they make sure that all the students get it, put a huge course reserve, sometimes 100%, and then the allocation of the remaining seats happens in the centralized phase of the allocation process. This is actually a huge problem because there is a huge amount of seats that happen that are allocated in the second part, that's centralized. And it, according to some estimates, it actually involves hundreds of hours of workers every semester. And at least, of course, thousands or tens of thousands of the foregone salaries or labor every semester, which shouldn't be the case. And that's what we argue why our centralized mechanism should be adopted, at least at some universities. But now the question is more practical. What course reserves to consider? Instead of considering actual course reserves, by the way, we also, of course, consider that, but the data, the results is really poor for our current process. We consider the optimal course reserves. In order to obtain the optimal course reserves, we're basically using the simulations we estimated what would be the optimal number of course reserves set using deferred acceptance algorithm. So basically, we run deferred acceptance, calculate the number of students who qualify for reserves, and this is the number of students ideally would be set. Since it can be random from run to run, we basically the average, and this is the optimal course reserves. This is, in some sense, this should be done if we use the past data on the enrollment. But yeah, so that's why whenever you will see comparison, is comparison not over actual mechanism, but a better version of random serial dictatorship with course reserves. So we can compare random serial dictatorship with optimal course reserves, and we consider as a benchmark because we believe this is the process that closest approximates the current practice. Our mechanisms serve the market with priorities and deferred acceptance with single and multiple tie breaking. Single tie breaking whenever we consider tie breaking for all courses simultaneously, multiple per course. And as I mentioned at the beginning, there is a huge tie breaking going on because there are only, say, 8 priority ranking per course, but there are thousands of students. In the paper, we also do additional simulations. I also have the slides for them. So if you're interested, so we consider the minority reserves where we only reserve a certain number of seats, or we provide the priority only for a certain number of seats. Probabilistic serial version of probabilistic serial mechanism for our setting. Just approximate competitive equilibrium from Eric Budish without any priorities. And approximate competitive equilibrium from incomes with Kludgy pricing, where we pricing set not exactly at the threshold, but a more smooth way. And of course, we needed to present random serial dictatorship result with actual course reserve. But this one is like the worst of what's going on. But I think it's also not fair to compare with it because we really do have in reality the second phase, which we do not model. Okay, 3 criteria. Then the percentage of students who prefer mechanism, the change in standard deviation of students' utility across students. So think about, Nicholas, Daniil, Patrick, and I were on the same level. One possibility is that Patrick got all the best courses and me all the worst courses. that will result probably huge inequality. But the better outcome is when both me, Patrick, Daniel, and Nicholas, they all get approximately the same utility. And that's captured in standard deviation of student utilities. And finally, the percentage of students who experience schedule envy. Let's go for the results. So this is, we consider random serial dictatorship with optimal course reserves as a benchmark. Now let's consider on the left 3 columns. So let's consider our mechanism, set the market with priorities. So this is the percentage. So first of all, there is a huge percentage of students per year of study who is indifferent. It makes sense. Remember, we are talking about only about 11% of courses who are contested. So it means that probably allocation will be quite the same for many courses. And that's why we have the huge amount of indifference. Approximately between 15 and 20 and 30% of students prefer our mechanism to random serial dictatorship, but also a quite substantial number of students do not. Initially, our results were much, we were very happy that we have a huge amount of the pseudo market with priority to prefer, but honestly, again, we are reporting exactly what we got in the data. You can see that for deferred acceptance, the number of students, or the percentage of students, even larger. So there may be much more students who prefer. 23 compared to 20%, 31 compared to also around 31, 25, 27, right? So more. But also the number of students who do not like, who prefer random serial dictatorship is much larger for deferred acceptance. Patrick, you have a question.
Do you also have some measure of the intensity of preferences in one or the other direction?
Yes, let me put it. Thank you for your question. Yeah, let me put it. So this is basically, this we also have intensity. So we, for year 1, say 588 among 1,500 students change their schedules, and the average increase in utility only around 3%. But for year 4, so you can see it's a bit between 2.8 and 6.4%. Does it answer your question? Good. Yes, so it's not huge. I can say it's not huge, but this is what we obtained from the data. Again, whenever we did first our best simulations without the data, we have much bigger numbers, but this is a benefit of doing empirical work. Honestly, the data really constrains you. You cannot manipulate anything. This is what you get from estimation. This is what kind of results you get. But one thing I want to emphasize that the percentage of students who do not like is the smallest among 3, right? And the difference between who prefer or not is the largest for pseudo market with priorities compared to all other mechanisms. So you can see deferred acceptance with single type break. This is approximately less 3%. Here it's 4%. Here it's only 2% the difference, and the same for all years of study. The difference between who prefer or not is the largest for our mechanism. But that's not it. This is not the full story. This is one suggestive evidence. But it also suggests that maybe using deferred acceptance with single multiple type breaking is not a bad idea. We also compare the standard deviation of students' utility by year of study. You can see that the standard deviation dropped between 8 and 6% for year 1 to 3, and it drops much less significantly for year 4. But it means it becomes more equal. So compared to all other mechanisms, our mechanism is tailored to fight unequal course allocation. And it does the best compared to others. But you can see also, say, deferred acceptance with multiple type breaking does do a quite good job. The percentage is smaller. In this version of presentation, we don't report standard deviation, but again, they are significant. Except maybe the 4th year, I think, right? The percentage, now also the percentage of students who experience envy towards students of the same or low priority. Well, first of all, for pseudo market with priority mechanism confirmed, the envy not more than one course. If you drop some of the courses, no envy at all. And approximately 10% students who experience this envy. Much larger percentages for random serial dictatorship with optimal set-asides. As you can see, it's around 77% only who do not experience any envy. For deferred acceptance, this larger number, but you can see also some students experience envy after 5 courses. Really, they really like some courses, and then you need to drop all the 5 in order to experience no envy. So this is exactly the situation with Anne and Betty that I talked in the beginning, where Anne got all the popular courses and Betty got none. We have much more data. We have information about the prices over subscription levels. We also compare it to alternative mechanisms again, and also we use different type of priority structure, where department first priority versus the year first hybrid structure, where that is actually used in some university, in some very few university, but it's used. And we also do some additional robustness check. Since I have only a couple minutes, so let me summarize and conclude. So we developed a deterministic pseudo-market with priorities mechanisms that allocates courses to students based on the student cardinal utility and respect course priorities. We show that this mechanism has nice properties in terms of stability, efficiency, fairness, and strategy proofness. And using simulations, we show that it delivers a larger utility to more students and a more equal envy-free course allocation. Using simulations based on actual university data. And again, I have 2 slides about benefits of pseudo-market implementing and potential challenges, but I think I will stop here